And with that, we head over to our next presenter here at Func Prog Sweden. Welcome, Alexander, to Func Prog Sweden.
Hello, everyone.
Hello.
Do you see me? Do you see my slides?
We see you, and I think soon we'll see your slides too.
All right.
We see your slides.
That's great. So I can start, right?
Yeah.
So, hello, everyone. I'm Alexander, and today I'm giving another kind of social talk because I am quite concerned with the social situation. Well, I could, in principle, give you a technical talk just because I'm an author of several technical books on functional programming. In particular, this one, it's Functional Design and Architecture, the first edition. I mean, self-published one. And my general goal as a functional developer is to shape a discipline of software engineering for functional design, for functional programming. Well, someone will argue that we have 40 or maybe 50 years of development in this area in functional programming, and you're talking about forming a software engineering discipline. Do you even think we did nothing for those 40 or 50 years? What ego do you have to reject everything that was done in this field? But I'll try to convince you that the software engineering discipline for functional languages has only started emerging recently, like maybe 10 years or so. So and why is that? And what do I mean saying those words, right? If you are interested in my technical ideas and approaches, I would encourage you to visit several of my recent talks on my YouTube channel. And today I will not dive deep into the details that much because we can speak about technical details for a long day and even more. But today we will talk about the whole discipline as a field. Do you know what's that? Do you remember this interesting device? I guess many of you know what is that, and that's a plane of the team called Rescue Rangers. And this plane was designed by a specific engineer. We know she's engineer because she does something that works and helps people to do their stuff, and she uses engineering approaches in several episodes of Chip and Dale Rescue Rangers. She were discussing how she does that. She does some planning. She draws some pictures to understand what she needs to do, and etc. etc. She uses some approaches. So in general, she's an engineer, right? And her name is Gadget Hackwarch in English. I would say the word hack here kind of indicative because yes, she is engineer, she is doing an engineer work, but it's kind of hacking. No one else is doing the same. She's unique, she is very creative, and the devices she creates, they are not serial, they are unique too. So yes, the question is, what is software engineering and how does it match with other engineering fields? There are mechanical engineering, like here on the picture, with cogs, wheels, and other gearboxes. There is electrical engineering, there is civil engineering, and finally software engineering. And we can find many various resources on what is engineering to people. Yes, those resources, those opinions don't really match don't really match. They people do not agree on what is engineering yet, even after so many years of various engineerings. But I'm quite interested in investigating what is this activity? How can we distinguish one activity from another, engineering from something else? So let's agree that everyone can call themselves an engineer with no limitations. I don't care if you call yourself an engineer and don't do any engineering or do it a lot. Call yourself whatever you want. The field and the activity we do, what interests me more. So what do we do as engineers? We do triple C. We construct, we control something, and we connect to something. This is not the exhaustive list of our activities, but still, in civil engineering, we construct structures, bridges, buildings. We control structural integrity. We don't want those things to collapse, right? We need to be very careful in designing those things. And we also connect to communications and external, communications, external providers, I would say, of something, for example, electricity. In mechanical engineering, we construct mechanisms. And we should control durability because, for example, rotational force can suddenly break something in your mechanism. So you need to be careful and you need to understand those dynamic interactions. You also connect to inputs and outputs. Inputs, for example, the input rotational force, and outputs is some indication or whatever it does. Electrical engineering, electronic devices, electrical safety, and connect to other devices. And software, finally software. We construct software, right? We should control something. Our privilege is to not always think about those limitations. We in some fields we have to think about safety, for example, for safety of not doing harm to people with our software. That happens, for example, plane software, right? Aircrafts and spaceships. They are driven by software, and this should not harm people. And sometimes, or maybe quite often, we don't need to know and don't need to think about complexity. But I would argue that this limitation of keeping our sight on complexity and not allow it to grow is one of main tasks of software design and software engineering as a field. All right. So we have objectives, we have restrictions, and we have external factors. Those three C to do as engineers. All right. So, but what is software engineering? What is it? What this field is? There are various articles on the internet, and one of them, "Are We Really Engineers?" by Hillel Wayne. Sorry if I'm pronouncing it incorrectly. The person, the author argues that those 6 points are misconceptions about engineering. Engineering is not when we're making something complex, and it's not when we are working in a part of as a team. And the author argues that it's not necessarily something physical for us to create and to name this engineering. Also, rigorous specifications and design documents are not essential to engineering, and mathematical principles are not essential to engineering, and also like loss of life and consequences do not define engineering uniquely. All right, and certification and license are not inherent properties of engineering. You can argue, you can have different opinions, and I quite agree and quite disagree with some of these points. Just for you to have some resource to argue with. What I'm interested in, how engineering is different from science and from witchcraft. And what do I mean? Witchcraft, and my point will be that functional programming is neither of these three, but maybe this three combined, or maybe one of them specifically. So let's move to what are those things. What do we do with engineering? We always, not always, often have a process and a methodology to follow and a language to speak in, complexity to control, right? Skill level to have an entry point into this field. There is something that drives our activities, and we want to achieve some result. Those are categories I want to consider. So what is the process? Development is the process. It's not just writing code. It's more than that. It's connecting to people, it's designing some architecture, it's writing documentation, testing, and talking to the clients. All of this is development. In witchcraft, from other hand, it's shamanism. A person sometimes jumps around a campfire and says some spells to summon, for example, a demon or something like that. And in science, we do research. There is some methodology we follow in engineering, whether it's civil construction or something else, and we call those methodologies design. It's a general term for methodologies. In witchcraft, there is probably some methodology, but we don't know about that methodology much. Otherwise, many shamans would be around us and they would be doing the same thing, but it's mostly a secret activity. They are making themselves isolated from the outside world, and sometimes they visit mountains and forests to do their shamanism, so that regular people should not be invited into that activity. In science, we also do research, trial and error, right? Language in engineering should be shared between all participants, because we need to move the needle. We need to create something that works for many people, and many people are involved. In witchcraft, only initiated can speak. You need to read some spell book and learn some occultism area or field to participate. Kind of the same for science, because it's not easy to understand scientific speeches if you are not much educated. Complexity in engineering, in particular in software engineering, is not welcomed, because we generally need to develop and evolve our software. Complexity is an obstacle for a successful evolvement of software. It makes every program too difficult to understand, too difficult to design, and sometimes needlessly so. And we, as engineers, usually don't welcome complexity. In science, complexity is everything. The current situation in science is that it's difficult to invent something simple. Everything simple was already invented. Low-hanging fruits all have been collected. So you need to be very deep into some difficult, complex field to advance the science. And this impacts skills levels. For example, in engineering, we want and we do we want to achieve a lowest possible level of skill to allow more people participating in our field, because we have many tasks, and those tasks are themselves very difficult. The more the world evolves, the more difficult tasks it faces. So we need more people in our engineering field, and we, as an industry, we lower the bar of participation. This includes more simple languages, more simple approaches, more simple processes, and etc. For witchcraft and science, this is not a problem at all. And probably you need to be an overmind to do science today. I mean, science is different, but the most valuable and most advanced science, right? What drives us in engineering? Pragmatism, of course. And this is the philosophy of achieving results with some limitations. We cannot just do things as we wish. We need to account many various restrictions and limitations. We should be pragmatic. Witchcraft is a cult, and science is curiosity. Finally, result in engineering is predictable. It doesn't matter what kind of software you want to build. If you have a picture in your mind and you think it will work this way, you can program it will work that way. Maybe sometimes you program it and see it will not be exactly as you wished, but still it's possible, right? Nothing is impossible, but maybe some vagueness there is in our idea what to build. Witchcraft is magic. We don't know the result. Maybe there are no results. And science is unpredictable because you don't know if your theory is correct, if your conjecture provable, and etc. and etc. Science is a very blind research area. You need to be lucky to find something and to make a discovery. And I would argue that in functional programming we have witchcraft, and a lot of functional programming is witchcraft, and this witchcraft is highly related to activities that look like mathematics, but they're not quite math. It's a very narrow application of mathematics to some parts of functional programming, and we need to be very specific to what exactly mathematical concepts we use and what we want to achieve with them. And look at that. There is shamanism. Why? Because there are people who are very involved into math theories, for example, category theory, and they know their stuff. Others don't. We don't learn some mathematical field to be capable engineers today. This is not a strict requirement, right? In general, now a person can be a former plumber, but still they will be able to participate in software development in some role. Mathematics is not necessary for our activities. We use mathematics a lot. For example, Boolean algebra, right? Calculations and many areas are very tightly related to mathematics, graphs, collections, and etc. But it's a tool not more difficult than counting money. It's kind of the same. In functional programming, however, mathematics is kind of omnipresent, not because this is the way it should be done, but because we are, as functional programmers, we're very interested in making it so. But as long as this situation persists, we are yet not in the engineering field, because doing mathematics in the way functional programmers do is not for everyone. It's a secret knowledge yet. Maybe because we have bad education, maybe because it's too abstract, maybe because the value of doing mathematical functional programming is not to make a result, and there is no intent to control complexity, but rather is to advance functional programming itself and maybe mathematics as well. So yes, doing mathematics is not bad, and applying it to all fields of our activities is not bad, but rather good. But it's quite far from engineering by those reasons you see on your screens. So let's talk about this witchcraft a little bit. Several examples of that. Abstract algebra. Abstract algebra has many notions that you can find in Haskell, for example. Monoids, groups, free groups, even my beloved free monads are from abstract algebra. And it's not a rare situation when you open some document in Haskell and it tells you about how monoids and groups are related together. And here is a mathematical theory for that. Now, you want to build some software, but you are being taught to some mathematical foundations of those ideas. Category theory is a complete, I would say, thief of interest in functional programming past years. Like in 2010s, it was mostly the subject in various resources to talk about. People were very enthusiastic. They absolutely loved this idea to apply category theory to functional programming, and they created tons of various libraries for that. Now, I don't say it's something bad. I use those libraries myself, for example, free monads, but I don't learn category theory itself, and I don't write code like those people do in those libraries, because this code is highly abstract. It's quite far from business domains, and as long as it's far from business domains, it's not easy to apply it in day-to-day tasks. So it's well applicable to library development and to data transformation, hence it's for functional programming, but it's far from our regular business tasks. Type theories, they are very useful in the sense that you can construct an interesting language and use it safely. For example, Haskell or Scala, those are the languages with great type systems. At the same time, the level of abstraction with types is very high, and over engineering of types is a known disaster of many code bases. And also, it's not something new. Mainstream developers, for example, C++ developers, have discovered the power of good type systems long ago. For example, in C++, there is the Boost library, a collection of various libraries, and it's massively type level in many its occurrences. So type level systems and type level programming is not something new. Still, it what dominates programming in functional languages, statically typed languages. But we have Erlang, we have Clojure, and they have own ways to express several ideas. One thing that is not kind of a subject or an area, but still something that people try to paint as a functional programming, as a true functional programming. Recursion schemes. To me, those things should not even be in a course of functional programming. We should not teach people to those things, because why? What's the problem of doing simple recursion or even doing loops? But those recursion schemes are super difficult and mind bending. So we talk about zygomorphisms, pretending that this is functional programming. This is certainly functional programming, but it's not the essence of functional programming. So I'm personally very concerned that we talk about that much. As I said, those theories are very abstract, and therefore they are very far from our business domains. And this light years gap has to be covered, has to be somewhat treated if we want to make those things to the right applicable to our day-to-day tasks. And the only thing that can fill this gap or if it's even needed, is some discipline, some methodology, how to apply those things. And only recently we started talking about category theory for programmers, category theory for day-to-day tasks, pragmatic category theory, and etc. And only recently we started writing specific and grounded resources, materials to teach people not to do mathematical like Witchcraft, but to do programming as we do it in the mainstream world. Just use those things as a tool, not as a thing to research, dive deep, and get lost for the world. I love showing this slide to my audience. Those are my Haskell buzzwords. Well, not quite mine, but still, those buzzwords are real, except one. Do you see what exactly one buzzword doesn't belong here at all? What is a personality disorder here? Can you spot it? Well, I don't really see anything like chat. Maybe you can show it in the chat. But all right, I'll show you without keeping the intrigue. Paranoid doesn't belong here. It's a personality disorder. From other hand, funnily enough, clown and joker are two terms from I don't quite remember, from abstract algebra or category theory, and they exist in some Haskell libraries as notions. Again, that's kind of a joke, but still people use it for some reason. I don't know what those things do, but they exist as programming notions. So people may say, the more math there is in engineering, the more it becomes engineering. My answer to that, the more math there is in engineering, the more it becomes math. My statement is at least correct and doesn't contradict itself. Maybe I can quickly talk about software engineering in FP as I see it, because it doesn't represent a ready field and it's still evolving. First of all, I think we need a structured and systematic knowledge for that, for design, engineering, programming with functional programming. Sorry for the tautology. For now, we have many distinct ideas, approaches, maybe applications of some cool things that do not represent and discipline. You cannot take something and start writing software from end to end, some methodology. You need to research topics again and again in functional programming. You need to discover things that do not represent a whole system. So this slows the industry down. This slows adoption of functional languages and makes it less engineering, and makes the impression that we only can be witches and wizards without letting more people in. Because if we had a systematic knowledge, it would be consistent. It would give you answers to all software engineering questions, and your risks as a business would be lower, much lower. We have some interesting occurrences of that. For example, in Elm, there is a predefined Elm architecture. It's given, it's there. You cannot avoid it. And this is good because, well, freedom of choice is certainly important. Some languages provide too much freedom, like Scala and Haskell and C++, but this freedom comes with responsibility. It's difficult to navigate. It's difficult to understand what you can use, what is not a very good practice, And what things you would avoid to avoid risks. Elm provides some vision. This is good. Being opinionated is not bad. We have several opinionated approaches like frameworks, and they are very, very popular because people tend to think less. In Scala, we can name the Zio framework, and the Zio creators say it's an effect system. To me, it's a framework because effect systems is another activity in functional languages that is being exported to the external world. And for example, they're trying to implement effect systems for JavaScript. Yes, another JavaScript framework. And there is a long story of effect systems in Haskell. For those who don't know what is it, it's an attempt to describe subsystems and effects, like side effects, like input output, in a way that could be combinable together. And mostly this resembles what we do with inversion of control frameworks in Scala, in Java, and in C#. So they represent some like idea, something like that. Another example is Erlang with its predefined architecture with actors. It's actors-based architecture. Again, it's given, and there are various practices how to use it. This is why Erlang feels more practical than Haskell, because it comes with an idea how to utilize it, how to use it, how to avoid problems, and how to solve those problems. So a picture how to use things is by definition a pragmatism, right? And we need this pragmatism in functional languages. What was also noticed that in Haskell in particular, maybe in other languages too, people do really want to know best practices, design patterns, and application architectures. This ratio between what people want to read about and what they are kind of maybe later, this ratio persists from year to year. There is a high demand for this pragmatic view of how to do functional programming. Unfortunately, we as a community are very focused on abstract things instead of providing this view. And look, the industry was started being formed in 1990s, and we've seen many various ideas emerging, and most of those ideas are about object-oriented programming or imperative programming, irrespective of the fact that functional programming was also there in those years. Haskell was born in 1990s. Lisp was one of the first languages ever. But we kind of failed to provide this pragmatic view. Take a look at those books. This only a fraction of knowledge that was created for languages, for mainstream languages. And only recently we started creating materials for functional languages. I know the reasons. I won't touch them right now, but the industry was dominated by OOP, not because OOP is better, but because we as functional developers are not very attentive to those happenings, are not very pragmatic. And this should be and has to be changed if you want to keep up with the industry. My personal feeling is that we can provide this knowledge, but maybe it's a bit too late for the industry because it's already formed. What do I provide personally? There are various methodologies like object-oriented design and test-driven design, and test-driven development, and etc. I want to form something for functional programming, functional declarative design, I call it. And this is a complete comprehensive methodology of doing things, and you can read about it in my books. So you can take it and you can develop an application from start to end using various ideas. There is a predefined architecture, there are design patterns, true design patterns for functional languages, not just use functions, you don't need to design patterns. No, we do have design patterns in functional languages. So and those things should be embedded into the whole picture. We also have functional interfaces in contrast to OOP interfaces. And being an interface doesn't mean automatically being OOP. Interface is a more general term. So we need to revisit our terms, especially from the mainstream, and see why they are useful and how they can be used in how they can apply it in functional languages. This is not a problem for Scala, for example, right? Or for maybe for F#. There is an integration with Java. There is an integration with .NET correspondingly, and we can fall down to Java's interfaces and C# interfaces. But in functional programming, we also have our own specifically functional interfaces to solve the same problems, to construct applications that are free from unnecessary abstractions and with several principles properly followed. So what is object-oriented design in general? It has design principles, it has ways to model and collect requirements, it has architectures, and there are development practices. You can see that those principles to the left are encapsulation, inheritance. Those are very related to OOP, but actually they can be used in FP. Encapsulation, not inheritance, more or less. Solid principles can be and are easily applied to functional programming, and the inventor of the solid, Bob Martin, tells about that too. But we as functional developers somehow reject the idea that OOP world could produce available knowledge. We are kind of isolated. We are better than them, and all those ideas do not belong to us. I do not support this attitude. So my approach is to revisit those design principles and ideas and architectures and apply them and provide an umbrella for doing stuff in functional programming the engineering way. You don't necessarily need to follow this, but having this discipline is a sign that we are mature enough to attract businesses. We have not a technical problem, we have a social problem in functional languages. Functional languages are unpopular because the industry doesn't believe we are capable of doing things. And one of such signs that we are capable is having methodologies and engineering attitude. We don't necessarily need to follow it, but we can have it anyway. Yeah, there are various design principles which can be applied in both OOP and FP, and also those paradigms are not highly and strictly separated from each other. There are moments in which those paradigms merge. We can name some practices in OOP, for example, anemic models that go closely with the FP ideas. There is one only step to reach FP from that. So those principles can be and should be applied and used for writing good code. Well, we have some approaches to architecture. This is only one of them. There are more. I'll skip this slide. We have approaches to interfaces, and we also need to understand there are two ways of doing abstractions, two kinds of abstractions: genericity-like abstractions and interface-like abstractions. In functional languages, especially strictly typed and statically typed. Genericity-like abstractions are seen as a silver bullet to solve everything, and you can open any, particularly any Haskell library, and you will see it's dominated by generic programming, generic types, some abstract concepts, abstract type classes and ideas. All those things are genericity-like abstractions. They are good for creating data transformation libraries and data transformation pipelines, mostly abstract. But in real tasks, we don't only need to transform data, we also need to have some extensibility quite often. And for extensibility of the type, there is a notion and there is another notion, and those notions can come in different times in the project lifetime. Now, genericity-like abstractions can work sometimes, but they provide too much complexity into that code, because extensibility mostly relates to domain notions, and genericity-like abstractions are very abstract. For this reason, we have not only generics in Java and C#, we also have interfaces in Java and C#, traits in Rust, in addition to genericity-like abstractions. In functional languages such as Haskell, interface-like abstractions do exist and are used, but they are not seen as such. There is no understanding that it can be used as an interface. It's not an OOP interface. It's a functional interface with functional properties. For example, free monads. Also, we need to distinguish the two notions, patterns and idioms. Patterns is something mechanical, some compound mechanism to solve a task, a mechanism sometimes to overcome the problems of a language. For example, a couple of design patterns from the Go book are overcoming problems in Java and in C++, like interpreter, yes, visitor, and something like that. But in general, it's an external mechanism to the task. It's not. It doesn't exist unless we invent it. From other hand, functional idiom is an inherent property of a notion. It's there. Whatever you do, it will always be within this notion. It will be attached to it inherently, and you may even not be aware of that. For example, a list, a functional list, it's a functor, it's a monad, it's an applicative. Also, it can be foldable and traversable. Those things can be found as properties of this list, but they are not an external mechanism. So we need to distinguish, and this will help us to speak in a more exact language, because when a mainstream developer asks a functional developer about a pattern, a design pattern, what patterns do you have in functional language? We feed that mainstream language with functors, applicatives, foldables, and they feel an internal friction, because they feel there is discrepancy between what they understand as pattern and what we understand as pattern. So I propose to carefully see the differences between patterns and idioms to have a meaningful discussion with the mainstream. And this is very important, because it's when pragmatism starts, we collaborate. I don't, that's probably it, but if I have more time, I have more slides here, maybe 5 minutes of that. So can functional programming be engineering? Yes, it can. Is it engineering right now? Not quite. It's close to that, but not quite. And do we need it? At least we need it for making an impression that we are capable. Because, I know there are developers who are fine with the current state of functional languages. But I am very concerned that we do not keep up with the industry. I want functional languages to be more popular, to be more industrial, because it's better for everyone. There is no bad in being open to the world, rather than isolated from it. So I have a couple more slides here. We can apply principles and ideas from the mainstream easily. Divide and conquer. We do have the same layers in our applications, absolutely the same application layer, domain model layer, persistence layer, and etc. And we can talk the same language. We can speak the same language as mainstream developers do. We need to have the notion of interface and use it mindfully, consciously. And there are various interfaces in functional programming. We can apply solid principles. There is a very it's essential how we can apply them, because as for example, single responsibility principle is an easy principle that we may avoid in functional programs, and may build programs more accurately, design them. We do it certainly, but we sometimes don't give it a description that we follow some principles. And people are very combative when we are talking about solid. It's not, they think it's an asset of OOP, which is not. So we can apply those principles as well. There are ways to follow OCP principles in various languages. There are various ways in Scala. You can use interfaces for that. In Haskell, there are ways to do interfaces on the type level, interface like abstractions. For example, this one. I won't stop on the code. The code doesn't matter. It's just an example. So technical details. If you want to know technical details, welcome to another talks and other materials. List of substitution principle is when there are several implementations of a subsystem, and violation of this principle means you cannot exchange one implementation with another, because a violator will do something differently than the contract expects, than the interface dictates. So it's easy to break list of substitution principle in FP2. Interface segregation principle. If we agree that we need interfaces, there is the need to segregate interfaces, and functional developers do, because many of them use effect systems for this reason, and combine those effects, they call it, I would say, in interfaces and subsystems in certain ways. Yet it should be understood as a activity we do both in functional programming and in mainstream. Dependency inversion principle can be applied. And actually, functional programming is quite full of inverting dependencies, because we pass functions as first-class objects into another functions. This is a form of inversion of control, the form of dependency injection. Low coupling, high cohesion, all those principles can be finally applicable to functional programming. There are universal design principles like least power, the Metrod's law, dump but uniform, or comes rather, no perfectionism, and certainly pragmatism. Let me skip those slides. Skip. All right, that's probably it. So we can and need to do it engineering way. That's my point. Thank you.
Thank you very much, Alexander. Thank you very much. You have given this quite a thought and put together all different concepts and put it into a string of cohesive thought, not just random thoughts.
Yeah,
Yeah,
yeah. I want to provide a system of knowledge, not just random facts and ideas. That's the point.
yeah.
Yeah.
Thank you very much. I immediately got a question here in the chat, like, will the slides be available somewhere? Will you put them out on your page or somewhere?
Yeah, absolutely. I'll just post it to my Twitter.
Hmm?
It's on your screens.
Cool.
And maybe somewhere else.
Yeah, yeah. We'll link it in the video description afterwards. We'll put them in there so people can find the slides, of course, also if they want to afterwards.
Mhm.
Again, thank you very much. How come you got into this field? Was it because you went to Haskell, worked with that, and then popped up questions, or?
How much time do we have?
Some minutes.
Some minutes.
Yeah.
All right. Well, I first was a C++ developer and was used to learn various languages like Delphi and C++ Builder and some others. And mm, I came to some ideas close to functional programming without knowing I do that. For example, I started creating domain-specific languages in C++, interpretable domain-specific languages, long before I learned Haskell. And my domain-specific languages were pure, they were interpretable, they were uh, declarative. And only then I realized that those ideas are not just some random ideas from nowhere, but they belong to one particular domain mostly. They are finally usable in C++ or C Sharp, or but still they have more meaning within a functional context. And I started learning Haskell by different reasons. Well, it was more than 10 years ago, maybe more than, it was 2010. It was 2010. And I realized that many things I do can be expressed using functional ideas, and they look like functional ideas mostly.
Mm.
And then I started wondering, if functional languages are so great, how can we apply them in real world practice? And I started asking those questions and realized there is a huge gap, enormous gap in functional languages, in the folklore about being pragmatic and about using those ideas in practice. So this is how I came to the idea of writing books, in particular this one, because someone needs to write something. I needed this knowledge myself. I needed to use Haskell uh, mindfully, consciously. I wanted to do it the right way, but there were no right way. There was a set of distinct ideas all flying around. So yeah, that's the story.
Sounds very reasonable. I have had like similar like experience starting out working. Get paid to make web pages, HTML, and then at some point you start realizing you need to start organizing your code. You need to have patterns, way of thinking. You can't just randomly code away. Yeah.
Yep.
Yeah.
Exactly.
Yeah. Again, thank you very much. There's a lot of people discussing in the Discord, so join there if you're interested to share your thoughts,
Yeah.
or anyone else's thoughts here, listening around OOP and FP. Yes. So thank you very much
Yes,
again,
sure.
Alexander, and thanks for joining us at Func Sweden. And with that,
Thank you
I would
for
like
inviting me.
you're warm welcome. Thank you very much, Alexander. And with that, we would like to thank everyone for watching tonight, or today, not tonight, daytime in Sweden, morning in US time zone, and evening in Australian time zone. So wherever you are, have a great day, lunch, or evening. Bye.